Okay, we are going to make some applications. Now, our first problem is about a sandwich structure. Now, let's see the effect of a sandwich structure on deflection, on deformation effect. First, we are going to solve the simple beam, simple homogeneous beam made of aluminum. So the question is like this: in the following sketch, a beam made of aluminum is simply supported at both ends and subjected at middle length to a transverse force of F is equal to 50 decanewtons, so 500 newtons. Calculate the deflection of the beam denoted as delta at the location of force F. So we have a rectangular cross section. The width of the beam is 10 centimeters. Its thickness is 5 millimeters. It's simply supported, and its length is given as 500 millimeters, and moreover it's made of aluminum. Okay, so the Young modulus is around 70 gigapascals. So let's first draw the free body diagram of the system. This is our beam. So we have a force at the center, F. Certainly we have two reaction forces because the transverse force is acting just at the center. Now what we are going to do is first we will calculate in order to find the deflection. Certainly this beam will make such kind of a deflection due to the bending, and we are going to find the deflection at the center. So for this purpose we need to write the stresses, in fact. So for a bending, stress at a point is moment at that location multiplied by the y. Y is the distance from the neutral axis divided by bending moment of inertia. Okay, so this is our stress. Now let's write the strain energy for this beam. In fact, remember that strain energy density at a particular location is 1/2 E sigma square. So this is the density, and we will integrate it over the volume. So let's say that this is W. Now I will substitute the value of the stress here, and I will decompose this integral into two parts. One is from 0 to L, and the other one is on the cross section A. So this is 1/2E. Let's substitute the moment here. So this is m square y square divided by I square dA multiplied by dx. So this is the volume. Now I'm just calculating the energy stored in the beam due to the deformation. Strain energy, total energy. and this gives me from 0 to L 1 over 2e. Now y square dA, integration of it over the area, because moment is constant at a particular location. So m is constant, I is constant, E is constant, so it's left with y square dA. Y square dA is the second moment of the area, so basically moment of inertia, and in fact we are left with this equation. So it is I for the total strain. So basically I need to determine the distribution of the moment through the beam. It is quite simple. In fact, as you see, I have two parts, and I can cut structure from either side in order to determine the moment distribution. So for this purpose, I can write the m, or let's do it like this. Okay, I begin to cut the structure from the left hand side. So let me show it. Okay, so first I will cut it from here. So this will be my first cut. Then I will cut it from here. This will be my second cut. So let's draw the moment distribution. I will omit the shear force at the moment in the cut. I will begin to cut the structure from the left hand side. So this is my moment. And this is the location of the cut, X. In fact, again I will omit the shear force from the diagram at the moment. So simply M1 is equal to F divided by 2 multiplied by X. Now I will make the second cut. So this is F divided by 2. This is F. This distance is L over 2, and this is X, and this is M2. Now M2 is equal to F divided by 2 multiplied by X, this distance. Now certainly this F will act in the opposite direction. This is minus F. This is X minus L over 2. And this will simplify to F divided by 2 L minus X. So this is the M2. So let me repeat it. I make the second cut here, so I put the F divided by 2. Here I have the F, I have the bending moment at the location of the cut. So I write the moment with respect to the cut. This is, if this distance is x, this is F over 2x minus F multiplied by x minus L over 2, and it simplifies to this expression. Okay, now I will write the strain energy once more. So remember that for the beam, the total along the beam, the strain energy is equal to 0 to L m x square divided by two E. E is the Young modulus, I x. So this is the formula for the strain energy. Now let me decompose this integral into two parts. This is 0 to L over 2 and 1 x square divided by 2EI plus L over 2 L m2x square divided by 2EI dx. Now if you do the integration by submitting the expressions for m1 and m2, so just put them into their places. 0 to L over 2, m1x is equal to f divided by 2x square divided by 2EI dx plus L divided by 2 to L f divided by 2 multiplied by L minus x square divided by 2EI dx. Now if you do the integration, you will obtain the expression for the strain energy. So the strain energy is F square L cube divided by 96 E multiplied by I. This is the total strain energy in the beam. Now we can, there is a theorem called Castigliano's theorem. Certainly it tells us something. In order to find the displacement at the location of the force F, we just need to take the derivative of the strain energy stored in the structure with respect to the force. So let's calculate the derivative of the strain energy with respect to force F, and in fact this will gives us the deflection at the location where force is acting. Certainly from here we will find the deflection as FL cube divided by 48 E multiplied by the bending moment of inertia. In fact, bending moment of inertia is 1 over 12 B H cube. This is with respect to the center of the cross section. So we know B is given in the problem. We need the Young modulus. In fact, so B is, for this problem, it is 0.1, H is equal to 0.0, it is 5 millimeters, yes, 0.05 meters, this is meters. So E is Young modulus of the aluminum is given to us. Sorry, just I will hold you for a second. Okay, sorry, the Young modulus is given as 75 megapascals. Sorry, gigapascals. So if you put all these values into this expression, what you're going to get is so let me repeat it once more. We have the formula for the delta. Delta is equal to FL cube divided by 48 E multiplied by I bending is 1 over, so moment of inertia is 1 over 12 B H cube. B is 0.1 meters, H is 0.05 meters, E is 75 gigapascals. In fact, L is already given to us. L is the length of the beam is given as 0.5 meters. Then from here you can calculate the delta. Delta is 16.7 millimeters. So this is the deflection at the center of the beam. Okay. So next thing is we find the solution for the problem. Okay, now let's continue with the next part of the question. Now, instead of having a beam just made of aluminum, what we are going to do is we will divide the aluminum plate into two parts. So just assume that you divide the thickness. Remember that the thickness was 5 millimeters, and we made a sandwich structure with cover plates that has a thickness of 2.5 millimeters each, and we have a core material. Core material is made of polyurethane, and it has the thickness of, so please correct it, here it is written 25 centimeters, but in fact it is 25 millimeters. So the thickness of the polyurethane core layer is 25 millimeters. Now let's see how the deflection changes for this problem. So we again use the same amount of aluminum, but we just add a lightweight core material which doesn't have significant stiffness. In fact, the shear modulus of the core polyurethane material is 20 megapascals. So let's read the question. By cutting the beam of aluminum by its horizontal midplane, we obtain two parts with equal thicknesses of 2.5 millimeters. Each half is bonded to a parallelepipedic core made of polyurethane foam, making the skins of a sandwich beam in neglecting the mass of the foam and the glue. The latter has quite the same mass as the initial beam. So this structure has more or less the same mass or weight, in other words. So the beam is resting on the same supports and subjected to the same load F. Calculate the deflection at middle length caused by F, denoted as delta prime. Compare with the delta value found in question 1. Take the shear modulus of the foam to be 20 megapascals. In fact, the core material has a 60 megapascal of Young modulus. Now let's solve the problem. Let's look at the solution for this problem. Now in fact we have the same more or less the same problem, but for this time we need to consider the shear stress because now we have a very thick structure and we cannot neglect the effect of the shear. So we can write the strain energy, the total strain energy for this problem as, so this is 0 to L one over 2 m square AI. So the mean value or effective value of the Young modulus multiplied by the shear plus this is 0 to L 1 over 2 K effective value of the shear modulus multiplied by the area. Area S is the area dx. So let's write the effective values. K is a factor, constant. In fact, we can write the K as approximately 1 over G C. EC is the thickness of the core material plus 2 EP plus multiplied by the B. B is the width, and in fact we can write the average value or effective value of the Young modulus multiplied by the shear. So that is or let's write the exact value. Young modulus of the plate multiplied by 1 over 6 B EP cube, 1 over 6 because we have two plates, right? The one is the upper plate, the other one is the lower plate. So basically this is 2 multiplied by 1 over 12 plus EP multiplied by B multiplied by EC plus EP square divided by 2. We will continue below plus EC. So the Young modulus of the core material EC cube multiplied by B divided by 12. Okay, now remember that EP is equal to 75 gigapascals. Core material has a Young modulus of 60 gigapascals. GC is equal to, sorry, this is megapascal, 20 megapascal, so more or less 1000 times lower stiffness, Young modulus, right? 20 megapascals. Okay, so the core material has a thickness of 0.025 meters. Width of the beam is 0.1 meters, and EP is equal to 2.5 millimeters, 0.025 meters. Now what we need to do is first remember that in order to find the delta, so for this case let's say that the deflection at the center is delta prime dW dF according to the Castigliano theorem. So this is the deflection at the center. Now this basically means that we need to calculate the shear force distribution. In fact it is quite straightforward, but I will just do it again. So remember that this was our beam. It is symmetric. We have two forces on either side and I have one force here, F. Now again I will cut the structure, begin to cut the structure from the left hand side in order to determine the shear force and moment distribution. So this is F divided by 2. I have V1, I have M1. In fact, M1 is equal to F divided by 2 multiplied by X, if this is my reference point, and V1 is equal to minus F divided by 2, or yes, so let's say this is T1 in order to be consistent with the problem. Now I will make the second cut. This is force F. This is F divided by 2. I have T2 and I have M2 here. So now I can easily see that T2 is equal to F divided by 2. In fact, M2 is equal to, I take the moment with respect to the cut, so F divided by 2 L minus X. Now I will substitute these expressions, into the force distribution, but let's do it with Mathematica in fact. Okay, so let's change the magnification to make it much more clear to you. Okay, maybe a little bit larger. Okay. Now I will calculate the moment. I have two different sections. So in the first part, my moment is, so the strain energy was 1/2 m square or let's Just a moment. I will hold you for a second. Okay. So 1 over 2 m1 square multiplied by, divided by average Young modulus multiplied by the effective value of the Young modulus multiplied by the moment of inertia. And the bounds of my integral is, for the first region, x is equal to 0 to L. This is okay. Now I will calculate the strain energy in the second part. So that is from L divided by 2 to L. In fact, this is L divided by 2. That's okay. Now 1 over 2 m square multiplied by the effective value of the shear modulus. Now I will continue with the strain energy of the shear. Again, for the first part, it is 1 over 2 effective value of the, I write it as kgs, it is k divided by gs, or let's say 1 over gs. That's okay, that's better because k is 1. So 1 over gs, 1 over 2, that is t1 square. Fine. Do I have something else? No. Now the bounds for the integral is from x is equal to 0 to L divided by 2. Now I will have the last part. T2 L over 2 to L. So these are my strain energy, but first I need to define the M1. So remember that M1 is equal to F divided by 2 multiplied by x. T1 is equal to minus F divided by 2. That's okay. M2 is equal to F divided by 2 okay, F divided by 2 multiplied by L minus x. And T2 is equal to F over 2. So these are my variables. Okay. Now I will write the strain energy, that is W. I will integrate it, and this is my expression for the strain energy. Now I will take the derivative of this one, the W with respect to F, this will give me delta prime. So basically my strain energy is, or delta prime is, sorry, let's write the W first. W is F square L multiplied by K multiplied by effective shear modulus multiplied by the effective area plus F square L cube divided by 96 multiplied by the effective Young modulus multiplied by the effective moment of inertia. From here I can calculate the delta prime. Delta prime is equal to dW dF, and that is F L divided by 4 GS multiplied by K plus F L cube 48 E multiplied by the Young modulus, effective Young modulus. Now if you put the values, what you're going to get is basically delta prime Now the deflection due to the bending of the structure is 0.18 millimeters, and deflection due to the shear is 1.04 millimeters, and as a total it is 1.22 millimeters. So we just made a very small change, and in fact we significantly changed the deflection, so we have a more rigid structure. So remember that delta is 16.7 millimeters when there is no core material. So we just add a light structure which is less stiff and in fact increase the thickness, and this gives us additional and significant improvement in the stiffness of the structure. So basically delta to delta prime is approximately 14. So we increase the stiffness of the, so basically the structure with the core material or sandwich structure is approximately 14 times more stiffer. Okay, our next problem is about helicopter blade. So let's read the problem first. Consider a helicopter blade attached to the rotor hub. So this is the hub, as shown schematically in the following figure. Okay, so we have a rotor hub, helicopter blade. It is turning in counterclockwise direction if you look at from the top. So it is hub to tip length is given as L, and the joint of the blade from the center of the rotor is given as L divided by 10. The chord length is given as C, and it is constant along the blade as is seen in the figure. Z-axis is just oriented with the aligned with the hub, and x-axis is aligned with the blade. The airfoil makes has an angle of attack of 7 degrees. It's constant. So this is the figure. Let's continue to read the question. The rotor characteristics are as follows: 3 blades, rotational speed 500 rpm, so the rotational speed is given. The mass per unit length of a blade at first approximation is assumed to have a constant value of 3.5 kilogram per meter. Okay, so this is the weight per unit length. Length is given as 5 meters. Chord length is given as 0.3 meters. The elementary lift for a blade element dx, so this is the elementary blade. This is the cross section of it. Is written as dfz. So the vertical force, the lift force, is 1/2 rho c multiplied by dx multiplied by cz, capital CZ, v square, in which v is the relative velocity of air with respect to the blade profile. In addition, the lift coefficient Cz at 7 degrees is given as 0.35. Air density in normal conditions, rho, is given as 1.3 kilogram per meter cube. So let's continue to read the question. We will not take into account here the drag, so the resistance of the air will not be considered and its consequences. Okay, the helicopter is assumed immobile with respect to the ground. Okay, stationary flight in immobile air. If we neglect the blade weight compared with the applied load and assuming an infinite rigidity, so it's non-deformable, the relative equilibrium configuration in the uniform rotation is as follows. So it makes a very small angle, theta. In fact, since theta is very small, you can consider that sin theta is equal to theta and cosine theta is equal to 1. Okay, because it's very close to 0. Justify the presence of the blade flapping angle theta and calculate it. Okay, this is the first thing that we are going to do. Calculate the helicopter weight, because we know the rotational speed and we know how much the blade can carry. So basically all the forces are in static equilibrium. Calculate the normal resultant on any cross section of the blade and at the blade root attachment area. So basically okay, so we are asked for the normal force here as a function of the coordinate x and total resultant force at this junction. Okay, the spar of the blade is made of unidirectional glass epoxy with 60% fiber volume fraction with R glass. Rupture stress is given. Sigma L rupture is 1700 megapascals. The safety factor is 6. It is also given. Calculate the following characteristics: longitudinal modulus of elasticity EL of the unidirectional, cross-sectional area of the spar for any x value, and at the blade root, total mass of the spar for the whole blade, okay, elongation of the blade assuming that only the spar supports the normal loading, dimensions of the two axes to clamp the blade onto the rotor hub, an alloy steel 30 NCD 16 has been selected. Shear failure strength T-rupture is given as 500 megapascals. Bearing strength sigma bearing is 1600 megapascals. Represent the blade attachment on the on a scheme. Okay, so this is our question. So let's begin the solution of the problem. Okay, so first thing is at the hub. So just a moment, let's return back to the figure again. Okay, so this is our design and we are asked for the angle theta. So this is the first thing that is asked. In fact, well, we have two forces. One is in the direction of the x, so that is centrifugal forces, and in the direction of the z we have the lift forces. And in fact we have a pinned connection, and at A, as you see from the figure, it will not, the connection, the support at A will not carry any moment. So the net moment, the sum of the moments has to be equal to 0. So basically this means that the forces, moments generated by the lift forces, which is in the z direction, has to be balanced by the moment generated by the centrifugal forces, which in fact the moment occurs because of this small angle, because centrifugal forces are in this direction, and certainly it has a component in the horizontal direction. So let's write the forces, moment equilibrium in fact. Okay, so now some of the moments in the z direction, let's say that I have a small force dFz. This is already given in the problem, which is due to the lift multiplied by x. In fact, this is L divided by 10 to the L. has to be equal to moments generated by the centrifugal forces. This is L. Let's say that a small change in the centrifugal forces is Fc. In fact, the distance is x multiplied by sine theta. So we have this formula. Let me repeat it again. So we have the Z, which is perpendicular to the blade. So the Fz is the unit force perpendicular to the blade, which is due to the lift, multiplied by x. X is the location of the plate from the distance from the hub, rotor hub. So in fact it varies from L divided by 10 to L, and this has to be equilibrated by the moments generated by the centrifugal force. So again, this is this will act along the blade, L divided by 10 to the L, and then x multiplied by sine theta, because there is a very small deviation from the chord length. So certainly we can say like this: if this is your plate, this is your hub, you have this distance is given as x. So we have df z, the lift force, which is perpendicular to the blade. Lift is always perpendicular to the blade, and certainly there is a moment, there is centrifugal force, and in fact this is dfc, and then you have this distance, which is x multiplied by sine theta. Okay, so these are the forces that acts on a blade element, and if we integrate it along the blade, as is the case in the formula, we will obtain the moment equilibrium. Now let's write the forces dfz and dfc. dfz is equal to, we are already given, this is 1/2 rho is the density of the air, multiplied by c. C is the chord length, dx is the width of the blade element, cz is the lift coefficient, and v square is the velocity. In fact, that is equal to 1/2 rho c dx cz multiplied by this distance. So this distance is x multiplied by cosine theta, multiplied by omega. This will give us the velocity square of it. So this is the element dfz. Okay, so this is the unit element. So in fact, remember that the theta is very small, so we can say that this is approximately 1, and then we can write the dfz as 1/2 rho c cz x square omega square dx. Now let's write the centrifugal force per unit blade element. So we have the unit mass dm omega square multiplied by the r. So r is equal to x minus multiplied by cosine theta. Again, we can say that this is 1, and from here we have omega square x multiplied by m is the mass per unit length multiplied by unit length. Okay, so again, if we return back, if we substitute these equations into the expressions into the this moment equilibrium, so dfz dfc x sine theta, we will obtain this expression: L divided by 10 to the L x multiplied by dfz. So remember that dfz is 1/2 rho c cz x square, and we have another x here, so this is x cube multiplied by omega square dx, and this will be equal to the moment generated by the centrifugal force. This is from L divided by 10 to the L, and that is equal to omega square. We have one x here, and certainly there is another x coming from the load arm, so that is x square multiplied by m, and for small angles sine theta is equal to theta. So this is our equilibrium equations. Okay. Now, if you do the integration, what we are going to get is 1/2 rho CZ multiplied by the C chord length omega square L to the power 4 minus L to the power 4 divided by 10 to the power 4, and that will be divided by 4. This will be the one side of the equation because of the lift, and this will be equal to theta m is the mass per unit length, omega square, that's the rotational speed, angular rotational speed, L cube minus L cube divided by 10 to the power 3, and that will be divided by 3. Now, if we look at this equation, so we know everything apart from theta, so certainly we can calculate the theta from here. Theta is approximately 3/8 rho C CZ divided by m multiplied by L. If you put the values, rho is 1.3, C is 30 centimeters, so it's 0.3, CZ is 0.35, M was already given as, sorry, where's the mass per unit length? 3.5 kilogram per meter. So the length is already given. Length is given as 500 meters, I think, no? So the length is given. In fact, when you put the values, all the values, what you're going to get for the theta is 0.073 radians. So it's a very small angle, which is at around 4 degrees, in fact. Okay. So we find the angle. Now, the second part of the question is about the weight of the helicopter. In fact, in this case, the lift force will be balanced by the weight of the helicopter. Therefore, we need to calculate the lift force, the total lift force. So if the lift is always perpendicular to the blade, and if this angle is theta, this angle is theta, so this angle is theta as well. Therefore, we have the cosine theta, which is balanced by the weight of the blade. So Fz cosine theta, or in other words, dFz cosine theta. If we apply the force to the unit length. Okay, so this is now we are going to calculate the weight from here. In fact, we will integrate the total lift force Fz cosine theta, and the limits of the integration is from L divided by 10 to the L, and this is the total lift force on one blade. So we can put the values. Again, cosine theta can be assumed to be 1. So we already derived the expression for dFz. From here we can calculate the net lifting force as 1 over 2 rho c cz omega square L cube minus L cube 10 to the power 3 divided by 3. So this is the lifting force. Now, since we have 3 blades, 3 Fz has to be balanced by the weight generated by the mass of the helicopter. So okay, now L cube divided by 10 to the power 3 is very small, so we can neglect it. Roughly speaking, this is approximately equal to 1 over 2 rho c cz omega square L cube. In fact, from here you can calculate the mg. If you put the values, so rho is known, c is known, cz is known, omega is known. Be careful, the unit of the omega is radian per second, and in fact n is given as 500 rpm. So mg is equal to 23,400 newtons. So this is the mass that can be carried by the blades. Okay, now what we are asked is the normal resultant force. In fact, we know that the normal force is mainly generated by the centrifugal force. Therefore, we will consider the Fc. So centrifugal force is always in the horizontal direction. Therefore, so let me draw it here again. So if this is my blade, so this is the Fc, in fact this is theta, and now I'm looking for the Nx. So I need the horizontal component, so this is the Fc multiplied by cosine theta. Okay, so let's write the Nx then. Nx is equal to from x to L, because it will, any cross section will carry the whole load, whole centrifugal load, carried generated by the mass of the blade from the point of X to the tip, in fact. So this is why we our boundaries of our integral varies from X to L. Okay, now this is the Fc multiplied by cosine theta. So cosine theta is approximately 1 again, so we can neglect it. From X to L, this is the Fc, and that's equal to X to L m omega square x dx. Okay, so we can calculate it. So if you do the integration, in fact, for an arbitrary location, n of x is equal to m omega square L square divided by 2 minus x square divided by 2, or m omega square divided by 2 multiplied by L square multiplied minus x square. So this is the normal force distribution acting on the blade. So at the blade root, where the force is maximum, in fact that is x equal to L divided by 10, what we are going to have is 120 kilonewtons. So this is the force which blade hub is subjected to. Now let's continue. In fact, what is asked next? Okay, we calculate the normal resultant force, and next we are asked for the longitudinal modulus of elasticity of the unidirectional fiber, unidirectional ply. In fact, we are given the materials. Just a moment, let me find the material property somewhere. There should be some material. Okay, so blade is made of glass epoxy with 60% fiber volume. So now we will calculate the longitudinal modulus for this configuration. In fact, remember that longitudinal modulus is equal to longitudinal modulus of the fiber face multiplied by the volume fraction of the fiber face plus longitudinal modulus of the matrix face multiplied by the volume fraction of the matrix face. Now it's a glass epoxy and it's made of R glass. So EF is given as 86 gigapascals, and EM, the Young modulus of the epoxy, is given as 4 gigapascals. Volume fraction of the fiber phase is 0.6, and in fact Vm is equal to 0.4. So we can calculate the EL as 86 multiplied by 0.6 plus 4 multiplied by 0.4, and the result is 53.2 gigapascals. Okay, now next we are asked for the cross-sectional area, and we already calculate the longitudinal modulus. We know the longitudinal modulus, and moreover we are given the rupture stress, so in the longitudinal direction. The rupture stress is given as 1.7 gigapascals. This is what is given to us. So at any and moreover safety factor is given as 6, and moreover this basically means that at any cross section sigma is nx divided by S of x. S of x is the cross-sectional area at a particular location of x, and this has to be equal to, this is the stress, 1700 megapascals divided by 6. 6 is the safety factor, so it has to be equal to 383 megapascals at a particular location. So S of x can be calculated from here. S of x is equal to n of x divided by sigma, and that is equal to, so nx is equal to nw square divided by 2. Then we have the 2 sigma multiplied by L square multiplied by x square. So this is the cross-sectional area at arbitrary location, and for at the root, blade root or hub, let's say S is equal to L divided by 10, and therefore the tip, so the blade root or the hub should have the area of 4.24 10 to the power -4 meters square. This is the area at the hub. Now let's continue. Let's calculate the total mass now. Blade of the mass of the single blade. Now we have the area. L divided by 10 to L. Density of the unidirectional fiber, reinforced composites, because we know the density of the glass, multiplied by S of x dx. Now S of x is already known as a function of coordinate. So mass of the spar is equal to from L divided by 10 to L, density of the unidirectional fiber, m omega square divided by sigma multiplied by L square minus X square. If you do the calculation, what you are going to get is rho u multiplied by m omega square divided by sigma multiplied by 1.7 divided by 6 L cube okay, so next we need to calculate the rho u. We will use the rule of mixtures for rho u, in fact. So rho u is equal to volume fraction of the fiber phase, density of the fiber phase, plus volume fraction of the matrix phase, density of the matrix phase. So from the tables or from you can find the density of the matrix phase and density of the fiber phase. If you do the calculation for the glass epoxy, what you are going to get for this volume fraction is 1980 kilogram per meter cube, and from here you can easily calculate the m spar, the weight of the spar. It is 2.38 kilograms. So the blade. Okay, now so we calculate the weight, total mass of the spar. Now next we are going to calculate the elongation of the blade. So for the elongation of the blade, you know that epsilon x, so the strain is equal to stress in the x direction divided by the EL, EX, let's say in the direction of the x. So this is equal to n of x divided by s of x multiplied by the EL. We know that n of x divided by s of x is equal to sigma. So this is 1.7 divided by 6 gigapascals, and that is divided by EL. And we find the EL already. EL is 53.2. So sigma is So epsilon x is equal to 383 divided by 53,200. So let's calculate the value. So the value is 5.3 10 to the power minus 3. This is the strain. Now we are asked for the elongation. So remember that we have a constant strain all over the blade, through the blade. So, and that is equal to this is the strain per unit length. In fact, delta L is then integration of the strain through the whole blade so from here we can easily calculate the value. The value is 2.4 10 to the power minus 2 meters. So this is the total elongation of the blade. Okay, our next question is about experimental measurement. Now we have a composite plate. Let's read the question first. Consider a unidirectional carbon epoxy plate from which two samples are cut as shown here. They are tested in a testing machine. Strain values are measured using strain gauges arranged as shown. Strain values obtained under different loads are linearized. Values corresponding to a uniform tensile stress sigma x equal to 20 megapascals are presented. Calculate the elastic constants of the unidirectional layer subjected to in-plane loading. So we have a plane stress case as is seen in the figure. So moreover, in the first sample, two strain gauges are fixed on the sample. One is in the direction of the fibers and the other one is on the perpendicular to the fibers, and the fibers are aligned with the x coordinate system. The strains are given as 143 10 to the power minus 6 in the x direction and minus 36 10 to the power minus 6 in the second one. And in this case of a second sample, the fibers are off-axis oriented. They make an angle of 20 degrees with the x coordinate, and again load sigma x is applied in the x coordinate system. In this case, the strain gauges measured values of the strain are 660 10 to the power minus 6 in the x direction and minus 250 10 to the power minus 6 in the y direction. Okay, so let me remind you the relations with the stress and strain for an anisotropic or orthotropic plate. Okay, now let me remind you some expressions, So the relations between the stresses and strain. In fact, we have the strain, then we have the compliance S, and then we have the stress. So let me write the strain. In case of we attach the coordinate system to the fibers, so we have the strain in the direction of the fibers, we have the strain perpendicular to it, so the transverse strain and the shear strain. Then we have the stress. Stress in the direction of the fibers, stress transverse to it, and the shear stress. Sorry, stress, yes, in the transverse direction, and then the shear stress. So let's write the compliance as well. We will use the matrix form. So this is 1 over EL. EL is the longitudinal modulus in the direction of the Young modulus in the direction of the fibers, minus mu TL, is the Poisson ratio, ET, and then it is 0. So this is minus mu LT divided by EL. This is 1 over ET. This is 0. This is 0. This is 0. And this is 1 over GLT. GLT is the shear modulus. Remember that compliance has to be symmetric, so therefore mu TL divided by ET has to be equal to mu LT divided by EL. So we have another condition. So this is the second condition that we have on the material properties. Okay, now in fact this is when the loading is in the direction of the fibers, or the coordinate system is attached and parallel to the fibers. But if we have an off-axis loading, then the situation is a little bit different. Now in that case, we use transformation. So for an arbitrarily oriented coordinate system, let's say this is xy, that is equal to tau minus y, inverse of the transformation matrix. So I will write the transformation matrix as well. Transformation matrix multiplied by the compliance multiplied by the transformation matrix itself multiplied by the stress tensor. Now The transformation matrix is made of sines and cosines. So it is cosine square sine square minus 2cs. This is the first row. Then this is s square c square 2cs, and then the last one is the cs cosine multiplied by sine theta and minus cs and c square minus s square. So this is the transformation matrix. In fact, c is equal to cosine theta and s is equal to sine theta. So one property of this matrix is the transpose of this matrix is equal to inverse of it. Okay, so these are the expressions that we have. Now let's use Mathematica for this. In order to solve the problem. Let me make the increase the magnification first. Okay, so let's define the stiffness matrix first. Stiffness matrix is a 3 by 3 matrix. So the first one is 1 over EL minus nu um, 1 over EL minus mu TL. Sorry for making you wait. Mu TL, and next one is 0. Now second row of the matrix minus mu LT divided by EL, and that's 0. And then the last row, this is the compliance 0, 0, 1 over GLT. Let's see it in a matrix form. Oh, I have something in the memory. Let me clear the memory of the Mathematica. Okay. What's the problem? I forgot to write. So this is, there is 1 over ET. ET is the Young modulus in the transverse direction. So let me clear the memory once more and then I will continue. Okay. Okay, now this is my compliance. Now let me write the transformation matrix. So remember that my fibers are making 20 degrees with the loading axis. So, and it is, I will convert it into radians. So it is 20 divided by 360 multiplied by 2 pi. C is equal to cosine theta, and S is equal to sine theta. I will leave it so. T, let me write the transformation matrix now. Transformation matrix is C square S square and minus 2CS second line, second row is S square C square 2CS, and last row is CS minus CS C square minus S square. Okay, so this is my transformation matrix. Let's look at it in matrix form. Sorry. So this is my transformation matrix. Now let me write the measured strain and stress values in vector form. So the strain that is measured in the direction of the fibers, or when the coordinate system is aligned with the fibers, for the case where the coordinate system is aligned with the fibers, I have the strain values. So okay, strain is 143 10 to the power minus 6, and then the transverse one, it is minus 36 10 to the power minus 6, and the shear strain is 0. Now I have the stress value for this measurement. So remember that it is 20, 0 and 0. So sigma L is 20 megapascals. Sigma transverse, so the stress in the transverse direction is 0, and moreover shear stress is 0 as well. Now I have the strain XY, so which is measured when the fibers makes an angle of 20 degree with the coordinate system. So the strain in the X direction is 660 10 to the power minus 6, and next minus 250 10 to the power minus 6, and 0. So stress is 20, 0 and 0. Okay, so these are the measured values. So let's calculate the strain. So remember that when you multiply the compliance with the stress, you will obtain the strain, right? This is stress LT, huh? Okay, now it's better. Sorry. Yes. Now. Yes. Okay. So it's S compliance multiplied by the stress, and we are given the strain. So this is the strain, and this shall be equal to the measured strain, and I write the calculated strain from the compliance tensor with small s instead of writing or let's say calculated. That's better. So this is the calculated strain. Now this has to be equal to the measured one. Strain LT. So the first component, for example, has to be the first I here is the index. Let me show it like this, maybe that's better. So strain 1 is this one, and strain calculated strain 1. Yes, I write the variable wrong. Is this one. So these two values has to be equal, basically. And then I will put I will be the index. I will use table command in order to make an iteration over the indices, over the elements of the vector. Elements of the vector change from 1 to 3, and this will be my equation set 1. This should be like this. Okay, so these are my equations coming from the first measurement. So as you see, I have 3 equations which are just functions of the longitudinal modulus and Poisson ratio in the nu LT. Therefore I have 2 equations, and I can obtain the longitudinal modulus and Poisson ratio from here. I will use solve command for this. Equation set 1. EL mu LT. Yes, mu LT. Now these are the solutions, so let's look at them in a numerical value. Okay, so the Poisson ratio is 0.25 and longitudinal modulus is 139 gigapascals, so 140 gigapascals at around. Now let's say that this is solution 1. I assign a variable. So I will get the values of the longitudinal modulus and Poisson ratio from here. So this is my variable. As you see, the curly brackets means that this is an array-like quantity. So I have one array here, then I have the sub-array here. So this is the first element of the 1, 1. And I will get this value. So this is the second element of this expression, because the first element is EL and this is the second element according to the Mathematica. You see? So 112 is the value and 111 is the variable itself. So this is the longitudinal modulus. Now I will assign the values for the Poisson ratio and longitudinal modulus. In fact, it is the same. Now this is my second element, so this is 1, 2, and I will get the second element of the expression, and this is solution 1. Okay, I assigned the values for the longitudinal modulus and the Poisson ratio now. I will continue with the off-axis measurements. So remember that it is transpose of transformation matrix. I already calculated it, multiplied by the compliance, multiplied by the T. This is my rotated compliance. Then I will multiply this expression with the stress in the stress that is measured. So this is my strain. This is the calculated one. So now I have the expression for the calculated strain. Now this has to be equal to strain measured, and each member of the vectors has to be equal. Again, I will use the table command. and this is equation set 2. Now I have the equation. Now I don't know the shear, I don't know the transverse Young modulus in the transverse direction and Poisson ratio nu TL. So I will use solve. Now I will solve equation set 2. I will begin with the shear modulus GLT, then ET, and then nu TL. That's the unknown. And let's see the solution for this. Okay, so it gives us an error. There seems to be a problem, but in fact there is one way of checking the correctness of the result. So we will divide this value, I will copy it here, to this one, and it has to be equal to nu TL divided by EL. If both values are same, this is nu LTL in fact. Now there's a problem in fact. So this is why we are given an inaccurate solution. There seems to be this is why it gives us a numerical error. Now I will do something else. Instead of using all the expressions, I will put an additional equation here, and then so first I will get the first equation from, and finally I will write this one, nu TL divided by ET has to be equal to nu LT divided by EL. So this is our last equation. So I just take out one of the equations, the last one, and then now I have two sets of equations, and in fact I know that the shear modulus cannot be negative, so therefore I will choose this set of equations as the answer. Let's check whether it satisfies the condition. Yes. So finally we have the result. So basically the shear modulus is 737.29 megapascals. The transverse Young modulus is 708.835 megapascals, and moreover the Poisson's ratio nu TL is almost close to 0.